Welcome back, everybody. So let's continue. Maybe we could start with this. Can anybody give me problems or at least limitations of hash indices? Because hash indices look wonderful, right? You get instant answers. What are the limitations? There has to be limitations.
There was actually a question on Zoom chat. Does any DBMS build hash indices by itself, or is this a Postgres intrinsic feature?
This is not specific to PostgreSQL. So hash indices is something that you are going to find in, I think, almost any relational database management system is going to have to offer hash indices, and B+3 indices as well, both of them. There's also other kinds of indices that we don't cover here, like geographic indices for locations in space and so on. But this is a very common feature that is absolutely not specific to PostgreSQL. If you go ahead with MySQL, Oracle, IBM, SQL Server, and so on, you will find also these features. The only thing that I have to specify is it's not automatic in the sense that you still have to declare the indices you want to build and instruct the engine to build it. It might be, though, that in some cases, some indices are automatically built. Many systems, actually, when you create a primary key, when you create a schema and you define a primary key, a lot of systems are actually going to build an index on the primary key automatically without you asking. This is very common. I think PostgreSQL, maybe you could look it up if you have a chance, Mark, on the documentation. I think PostgreSQL is probably also building an index on the primary key. It does? Is it hash or B+3, do you know? Maybe we could check that. So you see, you get some of them for free, like the primary keys are indexed. If you want to index something else than the primary key in the table, then you have to ask manually for PostgreSQL or the other engine to do it, right? But circling back to your question, that's absolutely not unique to PostgreSQL. That's a feature that most systems will have, right? Did I answer your question? Yes, awesome. And a follow-up question, yes?
Only in RDBMS or also NoSQL systems?
Also NoSQL systems, yeah. In fact, in Big Data for Engineers, we also discuss indices in the context of document stores. So this is actually something general enough that even the NoSQL system are going to have them as well. Yeah. But the NoSQL system didn't reinvent new things, right? They just use the similar indices than you have in relational systems, okay? You're welcome. Okay, so if there are no more questions, let's now go back to the hash indices and find out the limitations. Any ideas what the limitations could be? Drawbacks, costs, issues. I see, yes, a raised hand over there. Mark, you can bring the microphone.
Well, the hash indices are also just in a list, and if we have too many hash indices, it's just another list that we have to go through. So if the data is just so atomized that we have as many hash indices as parts of entries in the list, it isn't very useful.
Yes, so basically the point that you are making is that it takes a lot of space, right? They take a lot of space because when you have a lot of values, you need, so basically what we are saying is that this thing on the left is going to be very large, right? In fact, so in the case of a book, it looks like it's just like 5 or 10 pages in a book of 300 pages, but the indices here, they are not small. And in fact, if you don't want collisions, you need the table to be extra large with plenty of empty cells. So the cost is absolutely huge. So this is a very good point that indeed there is a cost in terms of taking space of hash indices. This is basically the compromise you're making. There is no free lunch. If you get something instant, you're basically getting time back, then you need to pay it in space, right? You exchange time for space when you do that. And that limits the number of hash indices you can build, which is, I think, the other point that you made, is that you can build many hash indices, but at some point you start filling up the memory. But then, okay, that's no problem. You can put them on disk. But here too, at some point, you can have so many indices that it doesn't fit anymore. And instead, because of the space, yeah.
Also on Zoom, somebody said memory space.
Somebody said
memory space.
Memory space, exactly. It takes space. Yeah, absolutely. So this is indeed one of the very big issues of hash indices. Okay. Another limitation. Maybe I can help. Here we use the query that is an equality. Oh, there is on Zoom. You've mentioned collisions. Oh, yes, maybe this is what you mean. So collisions are also a problem. Is that, again, here I shielded you from that by assuming that the hash function doesn't collide. In practice, hash functions can actually collide. So it means that you're going to have two values that are going to land in the same cell. And that actually forces you to have additional work and additional structures in order to resolve the conflict, which actually makes it a bit less good than just instant. It brings it back to in-between instant and logarithmic. So the collisions can indeed be an issue. You need a very good hash function. But again, if you have too many values, you're going to have collisions. So that's a good point as well. Another remark, if you want it to do.
Yeah, there's another question. If you wanted to do a where query for something is greater than or less than, can the hash function handle that?
Exactly. That's exactly what I was waiting for. So this is a great point. Indeed, if here you don't have an equality, but instead you have greater than, lower than, that doesn't work. That doesn't work. Because the hash function, all you can do is feed it into the h function, gives you a position that only works for equality. If you said, for example, lower than 19, what do you do with that? Because the hash function is a bit, it looks random, right? Just spreads the values all over the place in the hash table, but there is no logic, there is no order. So the only way that you could handle a query like century smaller than 19 is by computing h for 18, for 17, for 16, for 15, for 14, like all possible values. But as you can imagine, it's not, in practice, it doesn't work. You can just not do that, right? So indeed, hash functions allow you to accelerate selections on predicates involving equality. But as soon as you have ranges, it's called range queries, lower than, greater than, that doesn't work anymore. So this is a big issue, and this is exactly where the B trees, the trees and the B plus trees actually come into place to help, right? So no support for range queries. Not perfect in real life, that's basically the collision issue, and the space requirements for collision avoidance, right? By the way, the fact that hash functions are not perfect in real life, or that they are very hard to predict the output, this is why the blockchain and Bitcoin is actually working. This is the reason why you need billions and billions and billions of tries, or even quintillions of tries in order to get the hash function below a certain level. So the way that the blockchain works is that you have to try with plenty of different numbers, and you are accepted if the hash you generate that comes out of H is below a certain threshold. That can be lower and lower and lower to increase the difficulty. And because the hash function is totally unpredictable, this is the reason why the whole proof of work principle for blockchains. Yeah.
Just a small remark. So Postgres does actually index all columns which are unique or a primary key, and they do a B tree on them.
And that's B tree. Okay,
B tree, yeah.
Very good. So then not just binary primary key, but also unique. Very good to know. So if you add unique as a constraint, you also get then a tree index. So that means support for range queries with the trees. Okay. And space requirements. Okay. So let's get back to trees then. Let's try to have the range queries. So the first thing that you might think of is binary trees. This is something very popular in computer science. It's taught again in the bachelor's curriculum in data structures and algorithms lectures. In particular, the binary search tree would be a more appropriate name. The idea is that you have two children per node. This is why it's called binary tree, right? The idea of a binary tree is also that it's kind of balanced. So it's not like plenty of nodes on the left and then less on the right. It's more or less balanced. This is what gives you this logarithmic complexity, because the height of the tree is going to be logarithmic in the number of nodes in there, right? You do tolerate a bit of imbalance, like, for example, here you have a bit more on the left than on the right. We call it weight because you can imagine that you're holding that thing and that it's basically, leaning on the left or on the right. So you do tolerate a bit of difference, like at most 1, for example, but you try to balance things. This, for example, would be imbalance, right? In that case, if you try to hold that thing here, probably it would lean to that side because there's much more here than there is there, right? So in that case, that's not an acceptable structure. So you can, in that case, just rebalance. Okay. And the way that it looks like when you have these binary trees is that you put these values in there that are there for the binary search, right? For example, 4 is there, and everything that's below 4 is on the left, everything that's above 4 is on the right, right? So you go there, 2 is below 4, then you have everything below 2 is on the left, everything above 2, but still below 4 is on the right. Then you have 6, everything below 6, but still above 4 is here, and everything above 6 is there. So this is the constraint for a binary search tree, that you organize your, it's called nodes, these little rectangles, the nodes in the tree have numbers. And then when you search, you start at the top and then you go left and right as I showed you, right? Then you get logarithmic time, right? Okay, so everything that's smaller on the left, everything that's greater on the right, and it's recursive. You can do it with numbers. You can also do it with words, right? That also works. That's the way a dictionary actually works, because of course you don't have numbers in a dictionary, you have actual words, but then it's just what's called the lexicographical order, right? So in that case, everything that's before oath lexicographically is on the left, everything that's after oath alphabetically is on the right. Okay. And what happens typically when you have a tree like that is that all of these values in there have pointers to the actual rows of the relational table. And then these pointers are instants to be traversed, right? So logarithmic time to locate the value you're looking for by going left and right, and then you instantly follow the pointer to the record, right? But these are binary trees. This is the first idea that people might have, right, regarding that. You have a first design choice that basically says you have pointers everywhere. The second design choice is to only have those pointers at the bottom of the tree on the leaves. So the actual values are on the leaves. And the values that you have above are only there for the comparisons to go left and right, but they don't have any pointers, right? What that means with that second version, which is more popular, is that you start on the top, you go left and right, but you have to go all the way down until you select your value. And typically the values that you have on the top, so not at the leaves, but on the upper levels, they are just duplicates of the ones you have at the bottom. Because again, the only purpose of these values is the comparison, right? Or not and two, the three upper values, they're only here so that you know if you go left or right. And of course, that means that these are inclusive, exclusive intervals, meaning that, for example, on the left or is strictly before or, but on the right, it's greater or equal to or, right? So it means that you still have here the actual or with a pointer, but this or here is only for the purpose of comparison. And if it's equal to or, then you go to the right. Here, if you're looking for 2 and it's equal to 2, you go to the right as well and find it, okay? So it's a bit asymmetric, right? So the left is strict, the right is greater or equal. Okay, so when we say a B plus tree, technically, this actually means that you have only the pointers on the leaves and not above, right? But here's the thing, this is not a B plus tree. This is not a B plus tree because this 2 children per node thing is very inefficient. It's very, very inefficient. So we don't actually have 2 children per tree. We allow more children. So for example, here we could have 3 children, and then I have 2 comparison keys. So I have J and M here. Everything lower than J is on the left. Everything between J and M is in the middle, and everything greater than M is on the right. So you see how I can make it work with more children than just 2 children, right? For whom is that clear? This is how I get these generic actually B trees and B plus trees. Why do we want more children? This has to do with the way that the disks actually work. Because the index, when you build it, in the end, it's going to be stored on the local drive of your laptop or of the server that is running your database management system. When you read from the disk, you never read just one bit, 10 or 11 and so on. You actually read, to be more precise, something like 4,000 bits at a time, right? So when your computer requests data from the local drive, it's requesting like 4 kilobytes of data at a time. This is called a block. It's only reading in blocks. It's as if you would go to the grocery store, but you cannot buy individual fruits. You can only buy them in batches of 10 fruits, for example, right? So that would be then not a retail shop, but that would be a shop meant as an intermediate layer for the retail shops, right? So this is block access. It's reading in blocks. So for this reason, instead of a binary tree with only 2 children per node, this is more like what it looks like to be a B+ tree. It's multiple children at every node. In that case, you can see there's 2 children at the root and there's 4 children you see at the intermediate level. So you can see here, this intermediate node here has 4 children, 1, 2, 3, 4. So it has 3 keys here. Everything that's smaller before com is on the left. Between com and is the second one. Between is and merely is here. And above merely is here. Again, it's inclusive, exclusive, right? So this is strictly before com is here. Equal or greater than com, but strictly before is here. Equal to is or greater than is, but strictly smaller than merely is here. And greater or equal to merely is here. For whom is that clear? Okay. So multiple children, 4 children, 3 keys, 3 keys, 3 keys. So you see this is very regular here. So what happens, I have to remove that by opening, closing the chat so you can see what's written here. There you go. So all leaves are at the same depth. This is a constraint, right? It's like a genealogical tree where you have the great-grandparents, the grandparents, the parents, and the children, but all the leaves of the tree are exactly at the same level. There is no imbalance, right? So here the depth is 2, right? There is the first level with the root, a second level with 2 nodes, and then 1, 2, 3, 4, 5, 6, 7, 8 nodes that are leaves at the bottom. They're all at the same depth. Something else that you observe here is that there are constraints on the number of children. In that case, it's 4. But typically, you don't constrain as an exact number of children for B+ trees. You constrain as an interval of children. For example, you could say that the nodes have between 3 and 5 children. 3, 4, or 5 children, but not less than 3 and not more than 5, right? So 4 is between 3 and 5. But then you probably notice that 2 is not between 3 and 5, right? In fact, that's the privilege of the root. So the root is actually allowed to have less children than 3. That's the only exception. So here it's less, it's not more than 5. That's all we care about. But the fact that 2 is less than 3 is not a problem. Only for the root, only for the one at the very top. Okay, it's fine if the root has less. The values and the pointers are only at the leaves. This is why it's called the B+ tree. This is what I explained earlier, right? So this is why the colors are different. I put them in blue at the leaves, at the bottom, and the other ones are in gray. I'm repeating the terminology because since you're not computer scientists, it might not, I'm using the words like computer scientists use them, but maybe it's not obvious to you. What we call the leaves in a tree is all the nodes that don't have any children. So you see all of these nodes here. These nodes, they don't have any children. There are no more rows below. So these are called the leaves of the tree. And here they have children, so these are not leaves, these are called intermediate or non-terminal nodes. Right. It's very intuitive, right? Because in a tree, in nature, when you have a tree, the leaves, they don't have any more branches coming out of the leaves, right? This is where it stops at the leaves, okay? So in a B+ tree, the leaves that don't have any children, this is where you have all the values that you're indexing, and this is where the pointers are. And the values that you have here, they are only here for the comparison. They are only here to choose if you go left or right or to navigate the children. Okay, so when we pick an interval to allow the number of children, for example, between 2 and 4 in here, then we call that a 2-4 B tree or a 2-4 B plus tree. 2-4 means the number of children is between 2 and 4. Okay, 2, 3, or 4. Here I said B tree and not B plus tree because this is all colored in blue, right? So here the pointers can be anywhere. Okay. So an extra convenience that we have in the B plus tree is that we have extra pointers like this that we add. It's actually very convenient. This is for the range queries. It will become obvious later. Why do I add this pointer? Imagine that I start here, then I can go that way. I can basically follow the entire range of values like this. So in the case that, for example, I'm looking for everything that comes after Schultz, I'm here, Schultz. And if I want to find all the values greater than Schultz, look, tack, 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 tack. I'm just following the pointers. Makes it super easy to actually have the range queries. This is what you don't have in hash queries, okay? So the more general case, in that case, we said 2-4, but the more general case is parameterized as D plus 1 and 2D plus 1. So you can pick whatever you want for D. For example, if you take D equals 4, then it's between 4 plus 1 and 2 times 4 plus 1. So that gives you 5 and 9. Then you allow between 5 and 9 children, right? But again, that's a parameter. So it's up to you what you pick for the value of D. So of course, for the purpose of the slides, I'm picking small values, right? So here, for example, for D equals 2, it's between 3 and 5, right? But this is because it's easier to draw the slides. In practice, D is going to be much greater than that, right? It's going to be more like 100 or 1,000, right? So for example, you would have between 1,001 and 2,001 children at every node, right? Okay, but of course, again, for the slides, I pick smaller numbers. So the very small numbers, these are examples. So 1, 1 is for D equals 0, 2, 3 for D equal 1, 3, 5 is for D equal 2, 4, 7 for D equals 3, and so on and so on. Okay, so you need to make a decision when you build a B plus tree, you pick a value for D, and then you enforce the constraints on the number of children. But be careful, because the number of children doesn't mean the number of keys for comparison. If you have n trees, then you have n minus 1 intervals. For example, here, how many trees? 1, 2, 3, 4, 5, 6, 7 trees. How many intervals between the trees? 6, 7, minus 1, right? So be careful about that. That's the reason why if you have 3 children, then you have 2 keys. If you have 4 children, then you have 3 keys. If you have 5 children, then you have 4 keys. For whom is that clear? Okay. What that means is that if you constrain the number of children between D plus 1 and 2D plus 1, then the number of keys is between D and 2D, right? It's 1 less. Okay. Okay. So now I have an animation for you to show you how we actually build interactively a B plus tree like that. So we start like this. Imagine that I'm adding values. Just for the purpose of the example, I'm using increasing integers, right? But in reality, it doesn't have to be increasing integers, right? But just so that you see what it looks like. So I start with 1, then I have just one node that is the root, and it's at the same time a leaf, because that's the only thing there is. Then I start inserting values, 1, 2, 3, 4. And then since I limited myself to 4 values or 5 children, then I'm breaking the rule here. I have more than 4 values. What do? I split it. So I split it into 2 nodes, 1, 2, 3 on the one side and 4 and 5 on the other side. And then I put as a comparison value the 4, right? So 4, anything smaller than 4 is on the left. Everything greater or equal to 4 is on the right, okay? So now I'm okay because I have 3 values on the left that would be virtually 4 children, and I have 2 values on the right that would be virtually 3 children, right? So then I'm back to normal. Okay, now I add 6, 3 values, that's still okay. 4 values, that's still okay. 5, that's not okay. I'm breaking the rule again, so I have to split again. So now I'm taking 7 to do the split, and there you go. You see what's happening? I'm just splitting, and then I'm adding an extra value here, and now I have 3 children. So now I have 3 values, 2 values, so I'm fine. Then I continue, 9, 10, still fine, 11, again, I'm breaking the rule, there's now 5 values, that's too much. I'm splitting, so now I'm gonna split with 10, there you go. So now I have one, I have 3 values, 3 values, 3 values, 2 values, and I have 3 values on the top, so this is fine. Okay, now I fast forward. So now I fast forwarded, I added some more numbers, and I split again, adding this 13 here. And now I have this 17 here that I'm adding. So you see now, again, 5 values is too much, so I have to split. So I'm splitting maybe with 16 here. But now you see I only propagated the problem because now I have 5 values on this node and I cannot. So what do? I split again. And you see, this is how I get an extra level, right? Once in a while, I'm going to have to split the roots, and that adds 1 level to the tree. So you see how we started with level like a depth of 0. Now we have a depth of 1. Now we have a depth still 1, a depth of 2. There you go. And then if you continue, it just keeps increasing the depth automatically, right? If you delete, then it's the same thing. You might be below a threshold, right? So here it's still fine. Now we have a problem because 13, that's too few values. What do? We are going to merge nodes together again, right? Here I'm merging these 2 nodes, but then I have the same problem again with 16, so I have to merge again. So now I'm losing levels, right? So you can see, you can insert and you can delete values in an index. Now, you probably notice that it's not easy, right? The animation, it's visual, so you kind of get a feeling for what happens. If I actually asked you to implement that, that would be very tricky. In fact, even for computer scientists, we don't even do it in exercises to implement something like that. It's really, really, really difficult to implement and to get right. It's really a lot of work. And what also makes it more complicated is that there is no real standard way of doing that. So if you look at one system, PostgreSQL, for example, and then another like, I don't know, IBM and so on, there are many ways of doing that with different, it's like the dialects in Switzerland, right? So this is also one other complication, that there's more than one way of doing it, right? So I'm not going to ask you to implement that in any way. All I want you is to have the intuitive feeling of what's going on here, right? You just add values. When it's too big, you split. Then when it's too big, you split, and then at some point you split so much that you add levels, and so on and so on. And the other way around, when you remove values, then you have to merge back, and then that diminishes the level again, right? So when do you insert and delete values? Well, imagine in your database system, you have your table, you have your index, and people are going to insert new rows into the table. People are going to update rows. People are going to delete rows, maybe one at a time. Every time somebody adds a new row in your table or deletes a row in your table, you need to modify the index in real time to reflect the changes of the table. So this is why you have to implement the index in such a way that it's incremental, that you can add and remove nodes at will in the index, okay? Okay, and finally, what I wanted to show you when we have a complete index built is that typically what's gonna happen is that you store the entire index on disk, of course, but what you are going to do is that the upper part of the index, so the nodes that are at the upper levels, you're actually loading them into your memory. This, you probably wanna keep on disk, right? But this you load into the memory. Why do we load that into the memory? Because you might remember that the memory is much faster. It's much faster to read in the working memory of your laptop than it is to read from the disk. Why do we want to be fast here? Because here, this is where the comparisons happen. When you have a new value that comes from your SQL query, you need to compare it to know if you go left, if you go right, and so on. You want this to be fast, right? It's going to be logarithmic, but it's going to be even faster if it's in memory, right? So in memory, you do that. You just go left, right, left, right, left, right, and figure out what you read. And maybe you figure out that this is where you are between com and is, and that you need to read that from disk. And then, and this is where it's beautiful, is that all you read from disk is that here. This is what you load from disk, and then you read that into memory, and then you follow the pointers to the data. But you see, the beauty of it is that this you didn't need to read at all. You only need to read what you actually find in the index, depending on what the value you're looking for is, right? So again, that's on disk, and this is loaded in memory. Okay, so now I'm getting back to my relational table, to my system in PostgreSQL, or any other system, because again, many other systems also have these B plus trees. So now I'm going to build a B plus tree instead of a hash index, but on the same table as before. So what do? We start with 20. It's again the similar animation as I had before, 20, and I have my pointers, right, that I add. Then I have 19, that's good. Then I have -4. So for the purpose of showing you an example, I put a very small limit there. So it already is too large with 3. In practice, again, you could go to 100 or to 1,000 very easily, right? But for the purpose of my slide, I just decided that this is where I put the limit, and 3 is too much. So now I split it. You see, I added one more level. Then I have -6. So this is again too large. So I just reorganize. So I could also add a split up there, but I can also just choose to reorganize things, right? I just move over the 19 to the right, and there you go, right? Okay, then I have 20, and I'm done. So now I have a B plus tree. Of course, this is a ridiculous example with 6 rows and a super tiny B plus tree, but in practice, you can do that with 1 billion rows in your table and with a tree that might have 6 or 7 levels, right? Okay, and now how do we query that? Well, let's take a query. Now, you see, that's a greater than or equal now, because we can do that with B plus trees. How do we do that? Well, just look for the 19. What's the complexity of locating that 19 on a leaf? Linear, logarithmic, or instant? Okay, let's do a poll. Who thinks it's linear? Who thinks it's logarithmic? Who thinks it's instant? Okay, so the majority was correct, it's logarithmic. Because you start at the root of the tree and go left and right and left and right, and then finally land on a leaf. It's basically the time for looking up a word in a dictionary. So indeed, in logarithmic time, starting at the root of the tree, going left, right, left, right, left, right, you locate this 19. What do you do then? You basically start with this 19, and then you select all the values greater than 19, right? So you start with 19, and you take everything that's larger than 19, and then you follow the pointer. So you're going to follow this pointer, this pointer, this pointer, this pointer, right? Everything that's larger than 19, okay? And this gives you the results. And again, why is it fast? Because here it's a specific example where everything is there, right? But again, the reason why it's super easy to find everything greater than 19 is what I showed you earlier. Let me show you again. These are these magic things. Imagine that it's not 19, but it's it, right? And now I have to find everything greater than it. Thanks to these magical pointers here, everything that's greater than it, I just follow it like a snake here. I just find the path, and I just need to then follow all the pointers for all the values there, right? Okay. For whom is that clear? Okay. All right, so now I'm going back to the slides where we were. Okay, we build the index, and then we can locate all the values greater than 19, and there you go. Okay. So this is pretty much it. You have hash indices. They're super fast, instant, but they do not handle range queries and they take space. And you have B plus trees that handle range queries. They're a bit more compact, but it's not instant. It's logarithmic, but logarithmic is actually still great. Now, as I told you, and Mark actually remembered us, if you have a primary key or a unique column, you get a B plus tree index for free, right? But what if you want to build other indices on other columns that might not be unique? Well, you can do it with this special instruction. So you remember create table, create view, and so on. But now we also have create index. So we create index, we just give it a name, like you give a name to your baby. And then publications is the table we want to index. Title is the column in the publications table that we want to index. Then what's going to happen once you created that index is that this is an example here of SQL query that's actually going to be faster, right? By default, it's going to be a B plus tree. So this is going to be found in logarithmic time in the size of the table. For whom is that clear? Okay. So now a few words on that. What if you type that comment on the shell of a database on a very large table? What's going to happen? Two possibilities of what's going to happen. The first possibility is you press enter on creating the index, and then the entire system is blocked for 3 hours. You cannot even use it anymore for 3 hours. You can go for a coffee, for lunch, for whatever you want, but the system is unusable. Why? Because now the system is going to build the index and put all the resources into building the index. So it's offline. You cannot use it anymore. This is called synchronous index construction. The other possibility is that you press enter. It's not going to stop working. You can still issue queries and work with the system and so on, but it's going to be slower, right? It's just a bit slower than usual. It's just building the index in the background. It's using some of the power of the computer to do that. It's still allowing you to do queries a bit slower than usual until the index is over, and then you get again the full database to yourself, right? So this is again to say there is a cost in building the index. It takes time to build the index on a great table. You can either block the whole thing 3 hours, or you can just do it in the background and be slower. Some systems will allow you to choose between the two. You can even say, I want to block everything, but then it's going to be done faster. Or I just want the system to be a bit slower and do it in the background. Okay, but once you're done, and you issue that query there, the query will take very little time, super fast, logarithmic. This one too. You see, you don't know the value in advance, right? But whatever value you put is going to be fast. What about this one? So imagine you index the column year in the publications table. It's a B+3, because I didn't specify otherwise. It's a B+3. So I can support range queries, right? If I get a query where year is strictly higher than 1905, this I can do with a B+3. Right. But here's the thing. I have an end title, the theory of relativity. Title, it's not in the index anywhere. What do I do with that? Well, as you can imagine, we can still use the index. What are we going to do? We ignore for a moment this part. We just do year greater than 1905. This we know how to do. Just look up the 1905 in your tree in logarithmic time. Once you have it, traverse everything on the right of 1905, except 1905, because that's stricter. And then you follow the pointers. Then you have plenty of records. But then you need to remember that you also had that constraint, but that is something you can do later, right? You first ignore it, then you get documents, and then in the documents you got, you additionally test for that, and you eliminate the documents that do not satisfy that, right? So this query is not going to be super fast, but it's still going to be faster than if you didn't have the index. Right. For whom is that clear? Right. So in many cases, you will have a mix of both, that part of the query can be accelerated with the index and another part requires some extra work. And this is what we call post-filtering. We just filter the results after using the index. Okay. This is an example where the index is totally useless. Here we have an index on year, but we are looking for the title. This is totally useless. This is going to be linear time because I have to scan the entire table, right? Okay, now this one is fine because I have a range query on year with a B+3, so that works. And here again, that's an example where I can use the B+3 for the left part where year greater than 1905, but the end author Albert Einstein, I have to do it after I use the index as an extra step to filter out some results. Okay. Now, I can also index on multiple columns. What does that mean? It means that I first sort by year, and then I sort by author, right? So this also works. You can actually build B+3s in that way, okay? But not hash indices. Typically, the hash indices are in a single column. Okay, you can also control the order. So if you don't want the years to be ordered in ascending order, you can do it in descending order, meaning that you're going to have the recent years on the left, and then the older year on the right. So this is just like the order by of SQL, right? Okay, and you can say also nulls first, meaning that you're gonna have all the nulls at the very left of your B+3. Okay. Now I told you these are all B+3 when you do that. How do you get a hash index like this? Just say using hash of author, and then this is going to build the hash index on the author column. Okay. Now, there is a compromise to make, as you can imagine. Indices are not a free lunch. You might get your queries faster, but first, building the index might block you for 3 hours. But there is something else than that, is that when users actually add rows to the table or remove rows from the table or update rows in the table, it's a tad bit slower than it is without index. Why? Because every time you touch the table, you need to remember to also update the index accordingly, right? So the writing to the tables becomes slightly slower because you need to update the index, but the reads become faster, right? This is what you get with an index. If you don't have any index, writing is super fast because all you need to do is to update the table, but you don't need to worry about updating any index. There is none. But the reads are slower because you need to scan the whole table whenever you need to do that, right? So it's very important that you understand the benefits of an index, but also the costs of an index because there is no free lunch. Okay. So now in the exercises, I think you're probably also going to see this year. I want to very quickly show you the sort of things that you can calculate. In a real world scenario, you want to decide whether or not it's worth having an index. So you could imagine a simple scenario where you have two potential indices that you could build. We call them index 1 and index 2. And then people use the database, but you know that they will insert stuff in the table. We call that insertion 1. It's a pattern that people use to insert. And then we have two typical queries that people do, query 1 and query 2. I'm not showing what it is. It doesn't matter what it is. These are just queries such that the first query can be faster if you have index 1, and the second query can be faster if you have index 2. And then what happens is that you can do, it's like, you know, when you have a business plan and you create your startup, you can compute the costs of that. So basically you have these 4 scenarios. Maybe you don't have any index. What's going to happen without any index? Maybe you only decide to build index 1, but not index 2. Maybe you only decide to build index 2, but not index 1. Or maybe you have both indices, 1 and 2. So then you can compute. If you don't have an index, inserting is super fast. Just insert into the table. But Q1 and Q2, they will take forever because you need to scan the whole table. You don't have indices, right? Then you can compute for index 1. So here inserting is slightly slower because you need to update the index whenever you insert. But look, since we have index 1, now Q1 is super fast, right? So now the cost here is much lower. If we only have index 2, it's the same thing, but the other way around. It's Q2 that's going to be super fast. Q1, not so, still a full scan, but the cost of insertion requires modifying index 2. If you have both indices, then inserting is even slower because now you need to update 2 indices at every insertion, but now both of the queries Q1 and Q2 are going to be faster. Right. So you see, you have different scenarios. Here, insertion super fast, the queries are slow. Here, the insertion is slower, but the queries are fast. And then you can compute averages. But how do you do it? Well, it depends on the probability distribution in which the queries come, right? Maybe you have a lot of queries and very few insertions, or maybe you have a lot of insertions and very few queries, right? So you can just give them variable names as in math, right? A is the percentage of queries that are Q1, B is the percentage that is Q2, and then 1 minus A minus B is the percentage of I1, right? So this is just statistics. And then you can just compute the weighted average of these costs. So this is 2, 10, 10, 2, 10, 10, and you have the weights of the average, and that gives you the results. Then you can do it everywhere. And this is now when you can do your cost analysis. Is it really worth it to have an index or not? For example, when do we prefer to have 2 indices rather than none? Just solve the equation. And that basically tells you if at least 33% of your queries of what you do against the database is a query, at least 1/3, then it's worth having an index. If it's less than 1/3, meaning that you keep inserting stuff that you very rarely ask for anything, then it's not worth it, right? This is basically the idea. Okay, so I think you probably will have exercises on that, but again, I'm just going high level on that to show you the sort of things you can do. What is the main message here? I'm just saying it's not always worth having an index. It's really only worth having an index if you're very often going to use the index, right? So you have to, again, think of the costs of the index, not just in time, but also in space of storage. Okay. All right, I think it's time to stop here. This is the end of the lecture on indices and views. Next week, we look into data cubes. So thank you very much. Enjoy the exercise session and see you next week.